Good morning, everyone. Hopefully everything is on and live now. I hope you're all doing well and that you are ready for another super fun installment of Jugglebot stuff. I think this is a big week and I'm very happy to present to you what I will be showing today. And just before we get into that though, I want to do a very quick bit of housekeeping, which is to say that this is the last stream that I will do until the 12th of January next year. I'm going to be going away over Christmas and seeing friends and family and stuff, and it's just going to be easier to wait until then. So this will be the last one until then. Hopefully I'll still be able to get a lot done over Christmas, at least software-wise. We'll see, but yeah, this will be the last one until then. Before we get into the actual content of today, I thought it would be more fun to do a demo first. The first live demo of Jugglebot to date, which I'm a little bit nervous about, but we'll see how it goes. So here you can hopefully see my Linux screen and my actual screen of me, and I'm going to move the camera around. So that you can see Jugglebot as well. Let's go with that. All right. So I should just be able to launch my node. It starts off by going through a homing sequence where all the legs shorten until they hit the little end stops, and then rises up to halfway. And let me know if that screen, if the Linux screen is a little bit small. Hopefully it's sort of visible, and you can hopefully see the simulation, the plot at least, going at the same time. And now I can control it with my space mouse. So as I move my space mouse around, Jugglebot moves in exactly the same way. And it's actually kind of tricky to control it through the camera. But yeah, it works. And it's very exciting. I'm very, very glad that this works. So just to reiterate why I've gone to this effort, because I was able to control Jugglebot in this way a while ago, but this was using code that I was doing just myself. Now that this is over ROS, I can do really cool things, like if I move this plot out of the way, I can subscribe to the motor positions topic, and now I can just consistently get the data of where all the motors are. Never mind that these are negative, because I just need to make them not negative. But yeah, I can now get this data out, and my hope is that soon I'll make a user interface, and I'll be able to see what all of these legs are doing all the time. And so there's another topic, like if I stop that, there's another topic for the current in the motors, and I'll just be able to plot exactly how much current is in all of the motors while they're doing all of their moves, and I'll be able to see if the current spikes for some reason, and I'll be able to key that back to the movements that the Jugglebot was doing at the same time, to kind of see what was going on. It's really cool. It's a lot of fun to move this around. The first times that I moved this around, it was very nerve-wracking, and it took a little while to get all the accelerations right so that it didn't just like destroy itself. But yeah, now it works. RQT plot, I actually don't think I have. Does that just do it by itself? No, I need it. I need to install something, I think. I've done the RQT graph, which is cool. And this allows us, I showed this last, oh, what? Yeah, I showed this last week, and it can see, so I can see what everything is and what is being subscribed to what. It's a little bit tricky to see on this screen, but this is a really cool way to just see what is connected to what. But RQT plot, that didn't work. Is there some other command for that? I don't know. Either way, I was actually originally planning on doing a demo at the end, but I just figured that a demo at the beginning would be a bit more exciting. But so I will probably go back and do another demo at the end. For now, actually, I want to show you this. This is a cool thing that I like. So I spent so long this week getting to the point where I can quit my terminal and it will actually close Jugglebot down. And now it's all loose. so I can move everything around by hand, which is nice. But for some reason, so what just happened then, I don't know if you could really see, but all of the legs went right down to the bottom except for those two there. I have no idea why. It seems to be different ones, different times, but they don't go down the whole way. I'll potentially get into that later on if there's interest. But I don't really know what's going on there. That's always been the case. Because there's a flag, well, just while I'm getting stuff set up, I'll explain what I think is going on there. There's a flag in the ODrive like communications for like, is the trajectory, such a hard word to say, is the trajectory done? And I've just basically had like written a piece of code that says, if like move to the end stop, the 0 position, and wait until all of the trajectories are done. And then once all the trajectories are done, you should be at 0 and then you can stop. But what ends up happening is that two of them, reliably two of them, I don't think it's the same two, but it's always two because the one ODrive connects to two, will not go down the whole way. And then they'll spit out a bunch of errors about being overspeeded. And I don't know. It's very weird. But anyway, let's have a quick recap for what is actually going on here before we can get into how I've made this progress to get to actually be able to control it. So this is the sort of backbone of the ROS network that I'm using. And so we've got nodes, which are these blue ones, and these do all of the sort of like computation. All of the calculations and everything are done in the blue squares. And then they send their data between each other over what are called topics, which are these orange ellipses. And so, for example, what I was showing before, the motor positions, I was subscribing to this topic and I was reading out what those positions were. There's also another one that comes out of CAN handler that is the motor current, and that's the other one that I was just showing then before. And the really cool thing about this ROS network is that you can really easily add things in. So for example, right now, this is all just for like, everything that's on the screen right now is just robot control stuff. And again, I haven't done any of this stuff yet. That will probably be done over the Christmas break. But for example, I want to plot as well, because plotting is a very handy way to see if something is going wrong. And so I can very easily make a plotting node that I can quickly turn on and off if I want to. If I don't want to plot, I can just turn that node off. But if I do want to plot, then I can just turn the node on, and it doesn't affect the rest of the system. It's really cool. And so that because both of these two things, the Stewart platform and the plot, both of these need to know what the geometry of the Stewart platform is, I have a service that basically gets the robot geometry, which is stored in one central node. So all of the geometry is in this spot. So if something changes, I just need to change that one piece of code and everything else will update properly. And then that is transmitted over this service to everything that needs it, basically. And right now, I am controlling everything like this because, as I just said, I haven't done this stuff yet. So maybe I can bring myself back. Yeah, I haven't done this stuff yet. So what I'm actually doing is controlling it with the space mouse, which is this thing here. And then that data is going through the chain like this. And last week, and I can also add other things in as well. Like I can add a little dance pattern thing. I can add whatever I want to control the platform. Last week, I had done up to this stuff. And I wasn't really sure how to do the stuff out here. Namely, one of the big things that I was very unsure about is how to check for errors. Because I really don't want to be sending the motors commands that they can't physically do. Because as far as the motors are concerned, they can just spin as much as they want and nothing will happen. But of course, because of the fact that they are inside these linear actuators, if they go too far in any direction, then something will break. And I really don't want that to happen because it's really annoying, and it's been a while since something was broken, which I'm very glad about. I need one of those like days since last incident thing. That'd be pretty funny. But it's been a while and I don't want something to break. So what I have done is, someone suggested last week in the comments a very good suggestion, which I really like, which is to make sure that each little piece of code that's processing information and outputting information, it should run its own check to see if its output is erroneous. Like if its output is going to destroy something in any way, it should not send that data out. It should keep it and wait until it next has correct, good data, and then send that out instead. And that's really good. That seems like a very good way to stop errors from propagating through the system. And I've tried to model that a little bit in what I've done. So my first spot where I'm doing error correction is in this Stewart Platform Inverse Kinematics node. I'm setting in that node the limits of how long the legs can be. Sorry, my screen's just went a bit funny. I'm setting the limits for how long the legs can be, and it's basically saying if the legs are longer or shorter than this amount after doing this inverse kinematics, then truncate them. I'm not stopping them from being sent out. I'm just cutting them off at the limits, which has its problems. And I'm logging that as well. I'm logging the fact that they are hitting those limits. Yeah, we'll see how that performs when I'm actually trying to do juggling stuff. We'll see. And because I am very, very, very cautious of things breaking, I've also put in a second error checking thing here at CanHandler, which has, again, effectively the same limits, just coded differently. The first one in the inverse kinematics is the length, and in CanHandler it's the number of revolutions, but it's the same thing. And there's another check there for the same thing, basically. So if the limits are, if the data coming in is greater than what it can actually do, it will truncate it and send out this time an error being like, hey, this data should not have gotten to this point. How did this happen? Yeah, so I've got two checks, which does mean that if I change the actuators at all, I will need to update both of those, which is not really the best, but I hope that by the time that I change the hardware, my software is going to be a heck of a lot better, hopefully. We will see. So that was the first big question that I had, was how to check for errors. And the next one was how to do this, how to do the CanHandler node, because it wasn't trivial to me to think about, like, I've got this ROS network over here that's doing all the computation and everything, and then I've got this CAN bus over here that's doing the actual communication with the robot, and merging the two was not super trivial, I think, because I really want to be able to close the CAN bus cleanly. And what this means is that when I kill the service, like if I just turn everything off, if I hit my like emergency stop button over here and turn the robot off, I want everything to close cleanly so that when I start it up again, it doesn't have any sort of lingering effects from when it was previously running before, which did happen a lot when I was first working on the CAN bus. It was not closing properly, and every time I tried to start it up again, there'd be too many messages in the system and it'd all just get kind of stuffed up, and I'd have to like turn everything off and then restart the whole thing again rather than just the robot. So I need to be able to close the bus cleanly. I think I only need one access point. Well, I need only one access point. And I'm not too sure about this, and if anyone's familiar with CAN and this sort of stuff, I would appreciate if you could shed some light on this if you know the answer. But from what I can tell, it's sort of like best practice to have one node in the ROS network that's communicating with the CAN bus, rather than having multiple nodes all communicating with the CAN bus together. My only reason for thinking this is that it just seems neater, and also the fact that ChatGPT said that that was the case. ChatGPT is pretty good with this sort of thing, so I'm inclined to believe it, especially because that sort of makes sense. But it would be nice if someone could clarify that, because it would allow me to do some potentially different things if I could access the CAN bus with multiple nodes. But for now, I'm just sticking with only one. So my first thought was to have CanHandler as its own node. So all of the code would be in one spot. I'd have all the CAN code and all the ROS code just in one big file, and it would act as itself. But that very quickly got really messy. There was just too much going on in one piece of code. There were too many different things trying to happen at the same time, because the CAN network, as we'll see in a sec, the CAN bus and the ROS network, there's nothing linking them together inherently. They're not timed to each other. They're not like synced up at all. So having that all going on in one piece of code was a bit confusing. So what I have done instead is I've made a CanHandler node, which instantiates the CanHandler class. And that looks like this. So we've got the ROS network over on the left, and that's everything that we saw before. All of that stuff that we saw in that in the map before is in there. And then that communicates with the CAN bus handler node, which is a bit of a clunky name, but I guess it works. And this node is instantiating the CanHandler class, which is the thing that actually interacts with the CAN bus. And in this way, what we end up having, if we just kind of blur this in, then we end up having the ROS network communicates with this node just as it would with any other node, and then that node communicates with the CAN bus, which is pretty cool. But it was a bit of a tricky thing to think about how to get the data from the CAN bus to the ROS network, because these two networks are running completely asynchronously. There's nothing linking them together. And importantly, something that's really I really need to get out from the CAN bus is things like the encoder estimates and the motor current and that sort of stuff. And those messages are only coming in one motor at a time. And that was a little bit tricky to deal with. And so what I've done is within this CAN bus handler node, I am polling continuously to update the CAN handler. So at the beginning, I'm setting up a timer that runs 100 times a second. And every time it runs, it will call the CAN handler to fetch more messages. So 100 times a second, we're just seeing what new messages there are on the CAN bus. And because they come in asynchronously, these will come in so that there will be, every instant that the robot moves, there'll be 18, I guess, messages. 6 will be for the positions, maybe just 12. 6 will be for the positions, 6 will be for the current. So there's 12 messages coming in, all individually. And I have to sort those out to then send them off to the ROS network in a neat way. And the way that I've done that is to set up a buffer. So for example, for the position, just using the encoder estimates as the example, we have every single time that an encoder estimate comes in, it will have an axis ID. So this is like a motor number that it matches up with. So this might be motor 0 has data telling us that it is at position 3 revolutions or whatever. And we need to unpack that data. That's just because of the way that it's packaged in here. And then we add that to a buffer. And the buffer is a list of 6 values because there's 6 motors. And every time we get an axis ID, we fill in the buffer at that location with the data that we want. And then once the buffer is full, then we can send it off. So we make a copy of it so that it doesn't do anything funny after we've sent it. Then we send it off to the ROS network with this callback thing. And then we clear it again so that it's full of zeros. My only potential concern with this is that if, for whatever reason, one motor doesn't report its position when the other ones do, it's possible that the other ones could loop over twice or multiple times before the buffer gets filled with the one that's lagging behind. But I'm fairly sure that there will be other errors thrown before that happened. And this seems to be working really well. I've done this, it's been running for, I don't know, I guess it's not too long, but probably a total of 20 or 30 minutes. And it seems to be running fine. So I'm quite happy with that. And yeah, if you're curious, this is in the directory shown down the bottom. Yes, another thing that I was unsure about is how to handle the homing sequence. Because before, when I was just running this code myself, I just forced the code, the next line after initiating everything or initializing everything was just home the robot. And then after that, it did all the other interesting stuff. And that doesn't really fit super well in the ROS schema, at least the way that I was doing it before. And so what I've done is I've implemented a very basic state machine, and this is something that needs work, I think, but it does work for now. And what this looks like is this. So at the beginning, I have a parameter, a ROS parameter for is the robot homed or not, and it starts off false because it doesn't start off being homed. Homing, just to clarify, is that process at the very beginning that you saw where when the robot just starts off, it's in a random position and it needs to know exactly where it is in space. I could use absolute encoders, but I haven't been able to find any and I don't have them right now. So what I do is when the robot turns on, its homing sequence involves it moving down to the lowest position that it can possibly go in. And once the motor hits its end stop, the current spikes because it's pushing against a hard limit. And then once the current spikes, we detect that and recognize that, okay, the current has spiked, so therefore we are probably at the end. And that's saved as the 0 position. There are problems with this, I'm aware, but it works fairly well and I'm not too worried about it right now. Yes, so after we've homed the robot, we set that parameter to be true. And then every time we try to move the robot, we check if it is homed. And if it is not homed, then we tell the user that the robot is not homed, and we need to home it before we can move it. Right now, I'm just calling this at the beginning, pretty much what I did last time. But I'm trying to think of a better... I really want to make a user interface that I can use just to see all this information in one spot. But I'll get to that in a little bit. But for now, this works. There is, like, I could do this a different way where I don't need ROS parameters for this because all of this stuff is in the same node. So I could just do like an attribute of this node. But I feel like the parameters are a good habit to get into. I don't know. If you have familiarity with ROS and state machines, then I would love to know if this is kind of like a good system. But I kind of want to do it a bit more robustly because I want to have more states. I feel like having more states will be helpful. Like having one for, is the robot functional? Is it responding? Is the CAN bus active? This was something that I spent a long time on trying to handle when the CAN bus like malfunctions, which only really happens when the robot is either off or, well, yeah, it's either off at the beginning or if I've like hit the e-stop. That's the only time it really happens. But I would love for the network, for my ROS network to be able to handle that gracefully and kind of close everything down neatly, or try to like reinitialize the CAN bus and see like, hey, maybe this was just like a temporary power fluctuation or something. It would be really cool if it could like restore itself, but I haven't been able to get it to work. It's driving me crazy yesterday. I've seen some people suggest having a state machine node, like a full proper node that just keeps track of the state of the robot. And I've pondered this for quite some time, but I can't think about how to efficiently send the information to the other nodes. Do I use a service? Do I use a topic? Do I use parameters? I don't know. I don't really know what the computational demand of having topics is. Like if I have a topic that's just kind of sitting there empty 99% of the time, and it only sends a command or like a piece of data when the robot changes state, is that going to be like computationally intensive for all the nodes that are subscribed to it? Or will they just sit there and be like, no, nothing's coming in, so I'm not going to do anything? I don't know. And if you have any ideas about what states might be good, if you've got experience with robots, I would love to know, because I know that there are more states that will be handy, but I can't think about what they would be. So I've obviously got one for is homed, but I don't know what else to use. I'll go through the comments at the end, I think. So yeah, after doing all of this, it worked. And the first time I plugged it in, turned it all on, I was kind of surprised to see that it actually worked. But you might notice that the movements that are here are fairly janky and not really nice. And the reason for that is because I was noticing that what I was telling the robot to do was not what the robot was actually doing. And so you can see the simulation down here is not remotely similar to what the robot's actually doing. And this was very strange. To give you a full picture of, to give you a full picture of what was going on and see if you can figure out what the issue was. Up and down worked fine. When I moved the space mouse up and down, the robot moved up and down. Twisting side to side was reversed. So as I yawed in one direction, the robot would yaw in the other direction. And then pan, like moving from side to side, would result in the robot tipping to face the direction that I was trying to pan in. And then, of course, whenever I tried to tip the robot, it would pan in the direction that I was trying to tip in. And this has led me to create what I'm calling the first law of wacky steward platforms, which is if you have a steward platform that you have made and it's working and you're telling it to move somewhere and it's moving, but it's not doing what you want in a very weird and hard to figure out way, you need to check your mapping. And what I mean by this is you need to check that you have 6 motors and you're telling these 6 motors to be in a certain position. And there are 6 motors on the robot, and you need to make sure that your 6 over here that you're commanding are the same 6 that are over here, and they're not kind of twisted around. And you can see here, I have this schema that maps between the 0, 1, 2, 3, 4, 5 legs, and this sequence of like positions of where they actually are in the actual physical robot. The only real saving grace in my mind about this is that this is the 3rd time this has happened. The first time it happened, it took me like 3 days, and I didn't even realize what the problem was. It was a viewer on YouTube who saw, I posted a video of like what was happening, and they recognized what the issue was, and that took about 3 days. The second time this happened was about 2 months ago when I first had the CAN bus working. That took me like a day to figure out. And this time, when this happened like a couple days ago, it only took me like 20 minutes, which is great because it's happening a lot. I'm realizing what the problem is a lot faster than before. But it's just, I find it amazing still that when the first thing that came into my mind when this happened was like, where could this error possibly be coming from? This is such a strange thing. Up and down is fine. Tilt, or yaw, sorry, is reversed. And then like pan and tilt are swapped for some reason. Like, what the heck is that? But it was just the mapping. And fixing that meant that it now works completely fine. So now I can move it around as you saw before, and I'll probably have it up again in a sec. But moving forward, I think the code, the ROS network is getting to the point where it would be really nice to use a user interface to see what's going on and to be able to like click things and, for example, to be able to home it. Like right now, it's just when I run my launch file, it just homes, but I don't really like that. I would like to be able to have my ROS network be just running all the time and then be able to turn the robot on and off and be able to like, I don't know, have the hardware be kind of separate from the software, if that makes sense. And it feels like having a GUI would be a great way to do this. So for example, some things that I would like to plot right now in real time and to be able to save would be things like the leg lengths and the motor currents, just to see what they're doing. And in the future, I really need to be able to plot the trajectory of both the robot and the ball to make sure that they are doing what I think that they're doing. But there are so many options for GUIs in ROS. We've got RViz, we've got Gazebo, we've got Weebots, we've got RQT, and we've got Plot Juggler, and many, many others. And I don't really know what one would be best. It seems like RViz, Gazebo, and Weebots are more for simulating the physical robot itself and doing things like collision detection, which I really want to do. And if anyone has guidance on how to set that up with a parallel robot, I would love to know, because it seems like they're mostly tailored towards serial robots. But I don't think that they do the plotting of like topics and that sort of stuff as well. I'm not sure. If you have any input here, I would love to know, because this is something that I really want to do soon. But yeah, I reckon we can do another demo, because I'm sure there are people here. Actually, before we do the demo, I'll answer questions. Yes, brought to you by Dean. The Tripteron robot is something that my older brother sent to me a little while ago, and I really like it. It's a very crazy robot. It does not move the way that I would expect it to move. I really like it. Yeah. I know, Plot Juggler is... I'm kind of drawn to that just because of the name. So ChatGPT actually originally suggested that to me, and my initial thought was like, are you just hallucinating this because I'm in like my Jugglebot chat instance with you? But it's actually a real thing, and it actually does look pretty good, to be honest. Yeah, Puggle home service. That is what ChatGPT suggested. Having a home service that I can then call by myself. I think that I probably will do that, but I really want a GUI so that I can click the call the service button, and then that can do it. I think you're right with that. I think it's a good call. All right, so now we can see a demo from the actual proper beginnings, because before I kind of cheated and I had it on before I started. So welcome to my room. This is Jugglebot behind me here. And when I first turn it on, I need to make sure it's up a little bit, because when it first turns on, it needs to go through this initialization process. Something that's a little bit annoying with that is that it can... So what that was then is when the O drives first turn on, the motors, they go through this process to find what's called the index pulse of the encoder, and that way they know where in the encoder positions they are. It's a little bit annoying that it has to do that, but from what I can tell, it has to unless I have an absolute encoder, which I don't have, so I've got to do it. Yeah, once that's going, let's go onto my Linux screen again. We can start up the ROS network, and it should go through a homing sequence. Let me move the camera a bit. And it lifts up. And now I can control. So if I have my space mouse, I can like go down and it will go down. And like forwards is forwards. It's a bit weird because I'm holding it a bit strangely. Which is super cool. And I've spent quite a long time just kind of like, I love this movement. It's so satisfying. But yeah, I am extremely glad that this works now, and I love it. It's so much fun to play around with. And then of course, closing it down, same two again, those two again. They're not closing, and I don't know why. And they're throwing all these errors. So you can see like, overspeed. Why is it being oversped? I don't know. Who knows? Yeah, so the next steps are, oops, let me turn it off because the fan is loud. The next steps, I will probably not be able to do too much robot work over the Christmas break because I'm going like visiting family and stuff. But I will hopefully be able to do a lot of software stuff. And my thinking is that part of me really wants to do the GUI and to get like to make the robot a bit easier for me to work with. But part of me really wants to just kind of go for it because I am very confident that this hardware can throw a ball and catch it to itself. I know that that can work. And I'm very confident as well that with minor hardware changes that this will be able to do two balls in one hand. It might even be able to do two balls in one hand by itself as it is, but I really, like part of me just really wants to just kind of move forward and like chug ahead in that direction rather than focusing on the GUI too much. So I think I will probably honestly just focus on the ball prediction stuff, like just making Jugglebot juggle, especially while I can't access the robot too much. I think having the GUI might not be as easy to do unless I can actually like interact with the robot itself. But yeah, I've got some good plans for how to do the ball tracking. You can see I've got my little ROS network sketched out. It's going to be a little bit confusing. So we've gotten up to here, this one's done, and then all of this, oh, it's backwards. All of this stuff is all going to be new. So trying to predict where the ball is. And there's going to be a lot of stuff going on to try to predict where the ball is going to land. I currently only have open loop control because I don't have any other sensors in here, like the eyes and the laser gate, which I've mentioned a few times, but I just haven't like fully gone into yet, but maybe next year. Well, definitely next year. But yeah, it's all coming together. It's very exciting. And just before we go, I want to say thank you and happy holidays. I am very keen for next year. I might be able to get ChatGPT to make me a video of a robot juggler. This was the nicest one that I could find, and I especially like that. Oops. I especially like that the robot's got like a little star on his head, like he's a Christmas tree. It's quite nice. Cool. Well, thank you everyone, and I hope that you found this interesting, as always. And yeah, if you have any suggestions about any of this stuff, then please let me know, because I'm very new to ROS. I don't really know what I'm doing. ChatGPT has written most of the code that I'm using, and it works, but it would be nice to, I don't know, see if there's more proper ways that I could be doing things. I want to try to make this as like robust and like best practice as possible. So yeah, if you've got any thoughts, let me know. But if not, then thank you for watching, and I hope you have a very wonderful holiday period. And I will see you, whatever it was, 12th of January next year. Till then, have a good one.